All right. Here we are again. We're going to do section 6. This is magnetic force exerted on a single moving charged particle. We've looked at magnetic force exerted on current carrying wires. Okay. So this is a little bit different, but kind of similar. You're going to learn another right hand rule. Okay. Now, uh, again, I don't have my super colorful pens because I left those at the school, unfortunately, but that's okay. Um, there's an equation that relates magnetic force on a moving charge to the magnetic field strength. It's simply just F sub B equals Q VB times the sine theta. Okay. And the theta here, it's important to note that theta, okay, theta here is the angle between the velocity and the B field. Okay, so the velocity, right? A charge is moving in a field. This is the direction of its motion, right? Velocity. It's basically the angle between the direction of the motion and the B field. Okay, and all these variables are things that you should already know. Q is charge of particle. Okay, V is the velocity of particle. Okay, and then B is the B field strength. Okay, so those are all pretty straightforward. Okay, you do have another right hand rule here. This is again another one of these rules right here where you're doing your index finger pointing forward, your thumb points up, and then your middle finger points in a perpendicular way to your index. Okay, it's very similar to the one for the wire. It's actually almost identical. There is a slight change that is made with it though. So your index finger, okay, goes in the direction of motion. Okay, your middle finger is still the magnetic field direction. Okay, and then the thumb is still the force, the magnetic force applied to the particle. Okay, so if we look at the diagram here on the right side, right, your index finger points in the direction of the velocity vector, your middle finger points in the direction of the B field vector, and then your thumb is going to point in the direction of the force vector. Okay, it's very important to note that there is an important note to make about this right hand rule is that it may not always be right hand, it may be left hand. Okay, and it would be you would use your left hand, okay, for negative charges. Okay, you would use your left hand for negative charges. I don't know if you can see that very well. Here, I'll write over it, or I'll write it off to the side here. Okay, left hand for negative charges. Okay, so if you have negative charges, you're going to use your left hand instead of your right hand. Okay, oh gosh. Okay, all right. Moving on. Okay, this is an example. I showed a video of this in class. I don't actually have the proper like full demo set up for it, but I showed a video of this in class and how this works. So if you have a CRT TV, right? These are like really old TVs that have, if you've ever seen them, they're like really old TVs and they've got this really big, like kind of like box on the back of them, and what they do is they work in a kind of a funky way. Okay, they have this is the setup, right? This is kind of like a inside of it, and the reason they have that big box in the back is because they have to do this whole process before they can even show you what you want to see on TV. So the first step is that we start with this electron gun. Okay, and how does that work? The electron gun works through what it does is there's a filament. Okay, and it heats up. So the filament heats up, and electrons they kind of pop off the filament. Okay, so the filament will heat up, and electrons will kind of pop off of the filament. Okay, then what happens is that there's a potential difference. Okay, so when the the filament heats up and the electrons kind of fall or pop off of it, right? And as they're popping off, there's a potential difference in there that's going to then shoot them, right? So then electrons are accelerated through a potential difference. Okay. And that's where you go from the electric potential energy QV to 1/2 mv squared, right? So you're taking your electric potential energy and converting it into kinetic energy so that you can get them to move, right? Okay. And then finally, there's this deflection coil, and that's what actually is going to steer them. So the electrons, they're going to pop off here, they're going to accelerate, and then the deflection coil is going to steer them to where they need to go on the screen. Okay. And that's what produces the picture for you. Okay. So the deflection coil, okay, steers, okay, electrons to different points on screen. Okay, now that's how CRT TVs work. The older TVs, they don't really work like that. If I'm not mistaken, they don't really work like that nowadays. But they don't they don't have to do this whole thing anymore. Okay, but because they do this whole thing, you actually can notice some really interesting things with a CRT TV display. Particularly that because what's happening is you're popping off a bunch of electrons and then using a magnetic field to steer them, okay, you can actually deflect them again if you bring a magnet in front of the TV. And the stronger the magnet, the more that you can deflect them away. If you just search on Google CRT TV and magnet, you will see you'll see examples that people have posted of them with CRT TVs, and they take these magnets and they put them in front of it, and you'll see a couple of things happen. You'll see, first off, the picture will kind of distort. Okay. You'll notice that a lot of the videos I find are cylindrical magnets. If they use a cylindrical magnet, you'll see that the image is kind of twisted, or it forms these kind of weird circular lines. And then the bigger the magnet, eventually you can actually get black spots on the screen where there is no electrons hitting the screen at that point, okay? And that's because you've deflected all of the electrons away from it, okay? Then this example right here, I haven't really been able to find a good video for this, but this is kind of an example here where you have a television set, and if you bring these two magnets on opposite sides, let's say that they have the South Pole and the North Pole, okay, and they're both oriented the same way, okay, so these are like vertical magnets, okay, like you get that point, right? Okay. What happens is you would see that the magnetic field lines, right, they would go from the north to the south, okay? And what ends up happening is you would notice that the B field, so what's happening is the charges, right? The charges that are coming off of the electron gun are actually coming out of the page, right? So we would say that the velocity vector is coming out of the page, okay? Because the electrons are starting in the box at the back and they're coming at the screen, right? And we're looking at the screen, so it's going out of the page, right? Okay, so the velocity is out of the page and the B field is going to the right, okay? So what we would notice is, again, they're electrons, so we have to use our left hand, okay? So you have to use our left hand, okay? The B field is going to the right, and then the velocity is going out of the page. So the way that that might look is, I can't really twist my hand all that well. My index finger points out of the page. My middle finger points to the right. Can you see that? Okay. My middle finger points to the right. Okay, I can't really bend it very well. And then my thumb points down, which shows that the force on the electrons is also going to be directed downwards. Okay. And what that means is that you would ultimately see the picture shift down. Okay, so the image on screen would shift. So it doesn't matter. So depending on a couple of things, you would see that the image on screen shifts. In this particular case, it would shift down. It may switch depending on the orientation of the magnets, where the electrons are going. Right. I'm going to say that it shifts. In this particular case, it shifts down though. Okay. Okay, already did that. We already did the arrow to represent where the B fields are. Okay, we already did the poles. Okay, to test that, right? If we were to, for example, take out the television and leave the magnets in place, what you would notice is that the B field, how that works, is again this south north, south north. Okay, with these magnets, right? The north poles the magnetic field between the magnets is going from one to the next, right? Okay. But what you don't see is that outside what's happening is it's actually looping around. Okay. So what you would see here is that the north is actually going to be attracted to the south, but it takes a minute for it to loop around. So you're going to see that what happens is it goes all the way back around. Okay. Okay. Now here's the thing. Okay. So ultimately, you would notice that at point P, right, the magnetic field goes to the right. Point Q, it goes to the left. Okay, and so you would notice that, right? And that kind of makes sense with like if you know how the Earth's magnetic field looks. Okay, so what happens here? The explanation is that the magnetic fields, okay, they circle back to where they start. Okay. They ultimately circle back to where they start, right? So you'll notice the magnetic field lines started here at this magnet. They go, I think of it like, you're at an amusement park, right? And this is like you riding the roller coaster, right? Now you turn, and it was really fun. So you turn around, get back in line to ride the roller coaster again. But you have infinite amount of time. So you keep riding the roller coaster over and over and over again. Okay. Okay. Uh, Now, instead of using the two big bar magnets, we would instead use the cylindrical, and this one's the one that you can find videos of really easily on the internet. Um, but when you do that, like I said, you will see that the image kind of gets twisted. Okay, the image is twisted. Okay, and what that means for the image to be twisted is that what happens. So the motion of charges in a magnetic field. What does that mean, right? If the image is twisted, that means that the individual charges are undergoing. They undergo circular motion in a B field. Okay, they undergo circular motion in a B field. So if you have a charge inside of a B field, it's going to undergo circular motion as a result of that B field. Okay, okay. Um, to why do charges undergo that type of motion? Well, in physics 1, right, you learned, again, this is we were talking about circular motion. Okay. Well, in physics 1, we talked about how if you have an acceleration, right, that means that either the magnitude or the direction or both are changing in your velocity, right? Well, the magnetic field isn't changing the magnitude of velocity, it's just changing the direction, right? And that's because the magnetic force, okay, is always directed perpendicular to the charge's velocity. Okay. So what this is saying, okay, is that the magnetic force is only changing direction, not speed. Okay, it's not changing. Let me see if I can focus it a little bit better here because it's kind of bugging me. Okay. Um, it's only going to change the direction of the velocity, not the speed, right? And so therefore, the projectile will move at the same speed, the same magnitude of speed. It's just going to have its direction change. Okay. Okay, I'm gonna do a couple of these ones, and then I'll just show you kind of what I got straight from the key. Okay, you would use your right hand rule for each of these, and it would be depending on if it's the wire or the charge, right? So here's a wire. Okay, B field is going into the page, and current is going up. Okay, so use my right hand rule, and I would see that the force is going to the left. Okay. What about for the second one, right? Okay, again, B field out of the page, current to the right, and I can't twist my hand that far, but you would see that the force would be directed downwards. Okay. B field going to the right, current going up. Okay. Current going up, B field to the right. We would see that my thumb goes into the page, so the force is going to go into the page. Okay. Here, current is going diagonally up where the B field is going to the left. Now here's a fun fact, okay? So this current technically has a component that is parallel to the B field and then perpendicular to the B field. We only care about that perpendicular component, okay? So I would just point my finger in the direction of the perpendicular component of the B field. Goes there, and we would see that the force is coming out of the page. Okay. Okay, for the other one here, the current is going up, B field's going down. Notice that it's completely parallel. Okay, it's completely parallel. So the force on this example would just be 0. There would be no net force on the wire. Okay, let's skip down to the third line here. Okay, this is again a charge that has a velocity. It's diagonal, so we would actually see that it has a horizontal and a vertical component, except that it's actually not that hard, because what's happening, what you need to notice here, is that this is not a B field. This is an E field. Okay, so it's a positive charge. Positive charges always follow the E field. Boom. Okay, there's F sub. Wait, there's the force right there. Okay. Again, E field. Okay, note that. Make sure you read these carefully, right? E field. Okay, that's going to go diagonal up and to the left. Okay. Okay, down and to the left. Okay, so here we go. We're back to the wire, but this is in an E field. Okay, that's also important to note. It's in an E field. Okay. And understand that while there is current in the wire itself has a neutral charge. So therefore, it's not affected at all by the E field. Okay, wire has neutral charge. Okay, so F would equal 0. There'd be no net force there. Okay, I can't tell if you, I don't know if you can see that, right? Okay, charge moving to the left, B field moving up and to the right. Okay, there is, this one is a little bit harder to see, right? Because you would have to break the B field into components, I guess, right? So it would go there and then there. Okay. B field is going to go straight up. Velocity is going to go to, oh, sorry, this is a negative charge, so we're going to use our left hand, okay? Use our left hand. Velocity going to the left, B field going up. I'm getting that the force is going to go out of the page, okay? And again, I can't really show these to you because I can't like stretch my hand that far, right? I could rotate the paper, but you wouldn't be able to see it, okay? And then here in this example, you have a positive charge that has a velocity going into the page and the B field that's going up and to the right. So, okay, so this is positive charge, so right hand, velocity goes into the page, B field goes up and to the right. You would notice then that the force is going to pull up and to the right. Okay. Okay, to show you what the other ones look like, okay, to show you the second line of them, I'm just going to show you to you here on the key, okay? Again, into the page and to the left, right. Okay, right hand rule. You would see into the page, and then my thumb points down. Okay, sorry, I can't really show you the hand roll that well. I can try and zoom out a little bit here to help you, but I don't know if you can see it there. Okay, here again to the right, and then B field going down. So we would actually get the force going into the page. Okay. Here, this is a negative charge, so you'd have to use your left hand. Okay, left hand there, B field all the way around, so you would see the force goes into the page as well. And then negative charge right, you've got velocity going down, B field coming out of the page. You would find that the force is there using your left hand because that is a negative charge. Positive charge, again, you would have to break the B field into the components. Okay, and then when you point, let's see, B field's going has a component going to the right. Okay, so B field's going to the right. Velocity is going down, trying to like reorient it. Yeah, you should see that it comes out of the page right here, okay? And then right down here, okay, sorry, it's kind of bending because I don't have a ton of space for this. B field's going down and to the left. The current, this is a wire, the current is going out of the page, okay? So again, right hand rule up this way, B field that way, you would, I don't know if you can see that, right? You probably can't because of how high up the camera is. Force would go down to the right. There'd be no charge here because the charge is moving into the page. It's moving parallel to the B field. Here you see that again, it's moving to the left. This would be left hand rule, but this is an E field, so you actually don't need to even use the left hand rule. Okay, and you would get their force going down because it opposes the E field. Negative charge in a B field, it's going to go, B field's going up and to the right. Velocity's going into the page. Use your left hand rule because it's negative, and you get a force going up and to the left. And then here again, it's moving parallel, so it would just be 0. Okay. Okay. Okay, so there's that, okay. Let's look at these other two examples down here. Again, these ones are pretty straightforward, okay. So if we take a look, okay, the current here, so this wire here, right? You would have to use your right hand rule, your grip rule for the current in a wire, and you would see that it goes into the page on the right side, okay, and then out of the page on the left side, okay, and then once you figure out the direction of the B field on the left side of the wire, then we use our other right hand rule to figure out the direction, right? This is a proton, okay? So it's go, you know, so we use our right hand, velocity going down, B field out of the page, the force is to the left, okay? Same thing here. It's a proton, right? We figure out the direction of the current here. Use your right hand rule. Goes into the page on the left hand side, on the left side of it, and then out of the page on the right side. Okay. Proton again, so left hand rule. Okay. I can't really bend my hand again, like I said. Going to the right. B field out of the page, so we would notice that the force is going down. Okay. Here we have the wire going down again. It's going to be into the into the page left side, out of the page right side. This is an electron, so we have to use our left hand rule. You would notice that it goes in the right direction. Okay. Here, use your right hand rule to figure out the direction. Out of the page above, into the page below. Okay. And then the electron, you would notice again. You'd have to use your left hand for this. This would go up. Okay. And then for the last one right here, you notice it's into the page below, out of the page above, okay? And then you notice that the electron, right, so it's a left, you'd have to use your left hand rule because it's an electron, okay? And then the velocity is going down, you would notice that the force goes to the right, okay? And that would cause all of these particles to exhibit circular motion. I'll show you that here in just a second, okay? Okay. Now, here's actually where I'm showing you the circular motion now. Okay, the path that the charge takes in the field. Okay, again, use your right hand rule or your left hand rule depending on if it's positive or negative. Okay, so here our velocity is going up, B field into the page, so you would notice that the force would go to the left. Okay. And what that means is then it would take a circular motion that's going to look kind of something like this. And you might be thinking, wait, Mr. Mitchell, but the velocity direction is changing, right? The velocity's direction is changing. So wouldn't that change the direction of the force? No, actually, because if you use the right-hand rule at the top of the circle, again, okay, velocity's there, velocity going to the left, B field into the page, you would notice that the force is now going down. Yes, so the direction of the force does change, but it keeps it going in circular motion, okay? Here, out of the page, okay, out of the page, oh, it's a negative charge, so left hand, out of the page, B field out of the page, velocity to the right, you would notice that this is going to go, has a force going up, and then it's going to take a circular path like this. Okay? Okay, so then it would take the circular path like that, and it would keep going. Okay? For B, the charge is moving down to the right. Okay? Or, sorry, just straight down. It's a positive charge. B field out of the page. Okay? Then we would notice that the force goes to the left. Okay? And then it would go all the way around in a big circle. Okay? Okay. For the B field here, okay, this is going to be into the page, and then it's negative, so we have to use our left-hand rule, okay? Our velocity that way, B field into the page. We should notice that there is a force pulling down, and that's going to go in a circular motion like that, okay? Pretty straightforward, nothing too crazy here, okay? Okay, and then finally, this is an electric field, okay? So you have to keep in mind this is an electric field, okay? And what we would notice, right, is it's a negative charge, so the force is ultimately he's gonna feel the force going down, okay? And so he would actually travel in a parabola. This is like the projectile motion example that we considered last unit, right? Okay, so he would go in a parabola, okay? Okay. Earth's magnetic field, it actually shields the sun's atmosphere from charged particles approaching from the sun. And this is actually a really fun fact, okay? So the sun, right, the sun, shoots out these little particles. They shoot out charged particles, okay? And what happens is when the sun shoots out these charged particles, okay, they of course, go out into the solar system and kind of, fly out. And some of them approach Earth. And what happens when they do is they approach, and then the Earth's magnetic field actually deflects them away, okay? Actually deflects them away from the Earth's atmosphere. So they go, and they get deflected, right? So the Earth's magnetic field actually protects us from those, and that could actually be very dangerous if we did have a particle get into the atmosphere, okay? It could have a lot of unintended consequences it could have a lot of big consequences for like technology and stuff. So for example, right, we would say that as charged particles approach Earth, okay, as charged particles approach Earth, they are deflected, okay, by Earth's magnetic field, okay? They're deflected by the magnetic field of the Earth, okay? To do this example really quickly, right, if we have, let's suppose that we have a charge Q, mass m, moves at speed v in a uniform magnetic field B. The velocity of the charge is perpendicular to the magnetic field. Write expressions for each of the following. Well, the radius of circular path, we should know that mag force causes circular motion. So we're going to use our centripetal force, our centripetal acceleration equation from physics 1, okay? And we're going to set that equal to the mag force, okay? So magnetic force is just QVB, okay? And we set that equal to mv squared over r. That's our centripetal force equation. And you should notice, okay, that there's a v on the left-hand side, there's a v on the right-hand side, so we can cancel those out. We can make our lives really easy for us. You get QB equals mv over r, okay? And we want to get r by itself, okay? So we'll flip both sides of this, so you get 1 over QB, okay, equals r over mv, okay? And then when you do that, right, then you can multiply mv on both sides, and you get r equals mv over qb, okay, and there you go. Okay, that's all you have to do. The period of the circular motion, okay, you should remember that there is an equation that actually relates the period of circular motion and the velocity, right? Remember that velocity for circular motion, right, is if it's going in a circle, right, it's the distance divided by the time it takes to do that, right? Well, the distance around a circle is 2 pi r, okay? And then the time it takes to complete a full circle is the period, right? So it would just be t, okay? We don't know what t is, right? That's what we're trying to figure out. We also don't really know what r is yet either, but we do have an expression that we can use for it, okay? So if we replace r, okay, if we replace r with this expression that we just got, okay, then what we can do is we can get a new expression, which is v equals 2 pi over t, okay, times mv over qb, okay? And these v's are actually the same, so we can cancel those out just fine, okay? And that makes our life a little bit easier, because then we're left with 1 equals 2 pi m over qb, okay? And then we just need to get oh, sorry, I forgot the t right here. It should be the t right there too. Then we just need to get the period by itself, and this is literally the easiest step here. You just multiply t on both sides, and you get t equals 2 pi m over qb, okay? There you go. Okay, so there's that one. Okay, an object of 4 kilograms, so a 4 kilogram object carries a charge of negative 2 coulombs. The object is projected into a uniform magnetic field with a so magnetic field has a strength of 3 teslas, having an initial directed into the page, and it has an initial velocity of 6 meters per second to the right. The magnetic field exists in the positive x half plane as shown. Draw the exact path the charge will take as it enters and leaves the magnetic field. Units of the grid are in meters. Okay, well, the easiest thing to do is we need to figure out the radius of the motion, and we just gave ourselves an equation for that, right? So we can do r equals mv over qb. Okay. The mass of the object is 4, okay? The velocity is 6, okay? The q, the charge is -2. I'm actually just going to do 2 though, because radius, we don't really want it to be negative, okay? It doesn't really matter if it is or not. We just drop the negative at the end. And then b is 3, okay? And then when you calculate that whole thing out, okay, you should actually end up getting 4, 6, 12, 18, 24. You get 24 on the numerator. You get 6 on the denominator. You should end up getting 4 meters, okay, as the radius, okay? So what that means is that it's going to keep going, keep going, keep going, right? We know that. It's going to keep going. But then when the moment it hits that B field, okay, it's then going to enter a circular motion, and that circular motion will have radius of 4. So here's what I like to do. I'm going to, this is right here, count 4 spaces down. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And notice what I've done is I've marked the points where the radius is 4 so that I can just draw the curves here, okay, to create a circle of radius 4. So that's all I got to do. So this is the path it's going to take. It's literally going to enter and it's going to undergo circular motion. It's going to come right here, okay, and then it's going to curve back around over here, okay, and then the moment it exits the B field, it'll continue going straight to the right. Okay. It won't continue its circular motion because there is no magnetic force to continue the circular motion for it. Okay. Okay. Now let's say that a charge enters at an oblique angle. Okay. So it's an angle that's not perfectly parallel or perpendicular to the magnetic field. Imagine if it enters like this. Well, what's going to happen is this velocity has 2 components. Okay. It has a component that is parallel to the magnetic field and a component is perpendicular, right? Okay, I'm going to call this V parallel and V perpendicular, okay? What's going to happen is the magnetic field, okay, is only going to act on the vertical part of the velocity, right? Remember, it doesn't change the magnitude of the velocity, it just changes the direction, right? So what's going to happen is you're going to notice that the V perpendicular component, okay, or sorry, the V parallel component, let's focus on that one first. The V parallel component causes no force. Okay, so it stays constant. Okay. So the charge moves right with constant velocity. Okay. However, the vertical component does get acted on. The perpendicular component causes circular motion. Okay. So the circle would be perpendicular to B field. Okay, and how that might look is that what's going to happen is this is going to kind of spiral, right? It's going to go and it's going to, oh, can't even, my pen isn't working right now. There we go. It's going to cause a spiral. Okay, it's going to kind of take a spiral path. Okay. Okay, so there's that. Okay. And so the final example here for this section is there are 3 protons, 1, 2, and 3, all in a uniform magnetic field as shown. Okay, all of these have the same speed but move in different directions. Okay, and so we already figured out which proton should move in a helical path, right? It's going to be the one that's very similar to the last example, which would be number 2. Okay, notice how 3 has no component perpendicular to the B field, so it is not going to undergo any circular motion. There's no force acting on that velocity. So therefore, 3 should go in a straight line, okay? And then in a circular path, right? This one has all vertical component, and all of that's going to get acted on, so that direction is going to change. So it's actually going to make a circle that goes kind of in the plane, like perpendicular to the plane of the page. It would go kind of around, right? It's not going to go like, in this flat circle here. It's going to go like out of the page, into the page, out of the page, into the page, okay? And that would be proton number 1, which goes in a circular path, okay? This one is going to go in a helical path, okay? And then 3 is just going to go in a straight line, okay? Okay. The one that has the greatest radius, the circular path or the helical path, it would have to be the circular path, even though don't take my drawings for scale, okay? But it would have to be the circular path because there is more velocity component vertical for it to go in a greater path, right? Um, all v all v is perpendicular to b. Okay, so there would be more radius by the equation r mv over qb. Okay, that v would be the perpendicular component. And perpendicular to b field. Okay. Which one completes a full circle in least amount of time? Well, if we take a look at the equation for period that we derived earlier, right? T equals 2 pi m over qb. Okay. Notice that there's no dependence on v here. Q, the charges are all the same, the charges are all the same, masses are all the same, and B field is all the same. So the period is actually the same. So both of them would have the same period. Okay. Which one travels 1 meter horizontally in the least amount of time? It would have to be 3, and I hope that makes sense to you because this has all horizontal velocity. Okay. It's all horizontal velocity, which means that it would move the most horizontally. Which one has a velocity that changes? Well, 1 and 2 have a velocity that changes, even though the magnitude isn't changing. Okay, the direction is changing. Okay, direction changes. Okay, which one has a speed that changes? None of them. Okay, because B field cannot change the magnitude of velocity. It can only change the direction. The magnetic field does work on which of the charges? So if you remember from physics 1, okay, do you remember your equation for work from physics 1? It is the equation for work from physics 1, right? Work is equal to F d cosine theta, okay? Do you notice that the work done, right, at the angle is perpendicular, right? So if it's perpendicular, then or did I say FD cosine theta? It should be FD sine theta. I apologize. It should be FD sine theta. Okay. All right. Um, and then if sine theta, okay, is sine. Oh, so wait, hold on 1 second. It should be the bottom line is that it actually doesn't do work. Okay, because the B force is perpendicular to velocity. Okay. So it should actually be FD cosine theta. That's my bad right there. I don't know why I wrote it in the key as sine theta. I don't know why I did that. Okay. So it should be FD cosine theta because cosine of 90 is 0. Cosine of 90 degrees is 0. So work would be equal to 0. Okay. Okay. There's that. There's that section. All right. Have fun.